in centralized learning, we have the data, we train our model on the data, and then we deploy the model. However, in such an approach, actually, we have some limitations like data collection, the storage, or privacy in a way that we have direct access to the data. So the idea of federated learning is that if we have a bunch of participants with local data, instead of accessing directly the data, we send the model to the participants, and then they train the model under a local data set, and the server actually collects the model updates from the participants. So the motivations here are we can have more clients, more data, so we can have better model, and also privacy, but again in a way that we don't have direct access to the data. And there are different aggregation algorithms, and at the server side, we focus on federated averaging in this project. Then we have differential privacy with this formal definition that a randomized mechanism M provides epsilon delta differential privacy if for any two neighboring data sets, D1 and D2, that they differ only in one single record, the probability that we see A in D1 is less than equal e to the power of epsilon times the probability that we see A in dataset D2 plus some delta value. So here, epsilon is the privacy budget, and delta is the probability on which this epsilon, the upper bound, actually doesn't hold. We also have differential privacy in deep learning, or DPSGD, and the idea of DPSGD is that we limit the privacy loss per gradient update by clipping the gradients and also adding some amount of noise using a distribution. Okay, there are different variants of differential privacy in federated learning. We focus on local differential privacy and central differential privacy. So LDP, or local differential privacy, actually is a record level differential privacy, and CDP is a participant level differential privacy. So let's see how they work. So in local differential privacy, what we do is that each participant uses DPSGD to train the received model from the server on its local data set. And so after it trains that model, it sends back to the server. And in central differential privacy, server is responsible for that part. So basically, it bounds the updates that it receives from the participants, and then it adds some amount of noise to that bound value. So just to clarify here that CDP, or participant level differential privacy, is that participant level. What I mean by that is that if you get the output of the model from the server, and then one of the participants just opts out or joins the process, the output of that model shouldn't reveal such a thing. So here we see the algorithm for local differential privacy. So this part is like the federated learning process, but instead of using just training the model on the data local data set, they use DPSGD, which clips the gradients and then adds some amount of noise. And then in central differential privacy, this is different. So the server is responsible for bounding the updates that it receives from the participants, and then it adds some amount of noise. In both cases, we obviously use a moment accountant. I'm not going to into the details of that, but it's just for keeping track of the privacy budget that we use. Afterwards, we categorize the attacks in federated learning to two categories. So one is poisoning attacks, which they target the robustness of federated learning. And one is inference attacks, which they target the privacy. So in poisoning attacks, basically the adversary tries to reduce the accuracy of the model or make it misbehave on specific inputs. We focus on backdoor attacks. Backdoor attacks are like targeted model poisoning attacks, where the adversary tries to introduce a backdoor into the aggregated model. And for inference attacks, we focus on membership inference attacks, which the goal is to determine if a specific data point was used to train the model, and also the property inference attack, which the goal is to actually infer some specific attributes of the participants. So the way that backdoor attacks work in federated learning is, suppose we are in round R, and the attacker wants to introduce a model parameter. Here it's theta star, and for that, basically it sends a model update like this, and then at the server side, the aggregation would result something like this. And because at the final rounds, the model is going to converge, the second part is going to be very small value, and it results to have the backdoor model parameter at the server side. So the thing is that backdoor attacks are very easy to implement. I'll show in the experiments, and they're quite effective. It is difficult actually to control the local model that is submitted by the attackers. And any defense that requires actually investigating the training data set of the participant is not going to work because it's against the principles of federated learning. So in this work, we actually focus on two existing defenses, norm bounding and weak differential privacy. And the reason for that is that we see a potential for them to provide also privacy, not only robustness. However, we show that basically, theoretically and also in our experiments, they do not provide privacy against inference attacks. So basically, norm bounding is that the server just bounds the updates from the participants by some value. And weak differential privacy, it does the same thing, and it also adds some amount of noise. But the thing is that in differential privacy, we have the composition theorem, and all those epsilon values are going to add up, which results to a very large epsilon value, which doesn't provide privacy. For membership inference attack, we focus on the attack by Naseri. I'm going to explain very briefly that the intuition is that each data point affects the gradients of the loss function. So for example, if we have a task like this, and then we have a new data point which belongs to the blue class, it computes the gradients, and then it moves the curve to the opposite side of the gradients, and then if it goes further, basically it tries to correct it, and then at the end we will end up with the correct curve. However, if there is a new data point which doesn't belong to the class, nothing would happen. So the adversary basically performs gradient ascent instead of gradient descent on the data points that it wants to infer the membership. And then it observes if there's any reaction from the participants against such action. If there is no reaction, basically the curve would end up like this. And it knows that it doesn't belong to the training data set. And then they have different variants of this attack, active and passive, global and local. I'm not going into the detail, but the idea is that who performs the attack, like the server or participant, and etc. For property inference attack, we focus on the attack by Melis et al. So the attacker's goal is to infer some properties of the other participants' data set, and then at each round, basically, the participants' contribution is based on a batch of their local training data, and the attacker can infer the properties that characterize the target's data set. And for that, it needs some auxiliary training data, which is labeled with the property that it wants to infer. So for these inference attacks, the problem is the leakage from the model updates. And there are defenses like dropout or gradient sampling, but basically they don't reduce the accuracy of these attacks by that much. And we know that differential privacy is supposed to defend against the inference attacks, but there are no previous work that experiments that in federated learning. So the motivation here is that can we have both robustness and privacy in federated learning, and also if differential privacy actually mitigates the backdoor attacks or not. So for the backdoor experiments, we considered 4 data sets. For example, in EMNIS, the backdoor would be, so the attacker changes the bottom right pixel's color, and then it labels the pictures with that change to 0. Or for example, in C410, the attacker wants the aggregated model to label all the red cars as cats. And also for the word prediction task, the attacker wants to predict predefined words for some backdoor sentences. And for sentiment 140, basically the attacker injects a backdoor text into the tweet, and it wants the aggregated model to label that as negative regardless of the tweet itself. Sorry about that. We considered 2 different settings. We reproduced the results for norm bounding and weak differential privacy. And also in another setting, we tried to modify the number of attackers and see how the defenses that we have would react. So the defenses here are norm bounding, weak DP, LDP, and CDP. So I'll just present, for the sake of the time, I will just present the EMNIS result. So here we can see when we don't have any defense, the backdoor attack is working pretty good, figure A. Both norm bounding and weak differential privacy, actually they defend against a backdoor attack. And also, I mean, obviously it depends on the values that you use for the bound and also the noise that you add. But the utility is not decreased. The utility of the main task is not decreased by that much. However, if you apply local and central differential privacy with the privacy budget that you want, the mitigation is even better. However, and also it is expected that the utility is decreased. And also, so in setting 2, where we modify the number of attackers, we see the same pattern. But one very interesting thing here is that in local differential privacy, if the attacker somehow can opt out, so they don't apply differential privacy, the backdoor is kind of boosted in comparison if no one actually, none of the participants applies differential privacy. So the takeaways here are that both LDP and CDP can mitigate against the backdoor attacks. Also, another thing is that I should emphasize that the same epsilon value for LDP and CDP doesn't imply anything, because the privacy that they apply is in different level. One is at the client, one is at the record level. For the membership inference attacks, we considered these 3 data sets, like the Naseri et al. Paper. And we measured the attack accuracy as the fraction of correct membership predictions for unknown data sets. So what we observed is that, so basically here, global attacker is the server, and norm-bounding weak DP and CDP, they assume that the server is trusted, so that attack doesn't apply. So norm-bounding and weak DP actually didn't defend against the membership inference attack here. But LDP and CDP, they defend against the attack, so the baseline is 50%. You just guess if that data point is in the training data set or not. And also, the model was not destroyed, so the model converged. However, I mean, the utility was decreased. For property inference attack, we focus on LFW dataset. And the thing is that for property inference attack, local differential privacy is not meant to defend against the attack, because you can have multiple records with that property that you want to infer. And central differential privacy is meant to defend against the attack, but for this specific task, and because of the complexity of the model, we couldn't defend against the attack and also make the model converge. So when we increased the epsilon in CDP, the model was converged, but the attack was not defended. And when we decreased the epsilon, the model was not converging. So it remains an open problem there that CDP and DP didn't defend against this specific property inference attack. Those are the takeaways, and that concludes my talk.
Okay, next one, speaker.